Okay. So, we will continue from the where we stopped. We said that we will look into that alternative fuel, that small calculation we did, we will relook into it. Last class when we finished, we just were doing that. So, first thing is carbon emission from alternating fuel. If you are using agricultural waste and biomass, then it is already been taken into account. How? Because this agricultural waste won't need additional land for carbon dioxide capture. See, when we calculated carbon land, if you remember, is the land required to absorb this carbon dioxide. So, you will have to have plantations which will absorb the which will absorb those carbon dioxide, all right. So, that is the carbon land. Now, agricultural waste they would go into the ground, mother earth, and in future they would have got converted into carbon or coal or whatever it is in some form of fossil fuel. So, therefore, this is this is not accounted for in calculation of carbon emission calculation from the fuel, while fossil fuel, if you are extracting out let us say coal from the ground, or you are extracting say crude from underground, then that will add additional carbon dioxide to the atmosphere, while this one will go down, right, and possibly if they would go down, this in accounting we just do not take them. So, they are the kind of future coal or fossil fuel that you are using right now, because right at the straightforward at the time you are using. So, additional is not required for that. So, that is what it is. Now, supposing I have a like say 0.16 kg of coal, at this is required to produce 1 kg of clinker, that is right. So, in that case 160 kg. So, 0.616 kg is required to produce 1 kg of clinker. Now, that is 160 kg per ton, because we said 100 to remember, we said 100 to 200 we need kg per ton we need for production of clinker. So, this is that we have taken 160 kg. Now, for 1 kg therefore 0.16 kg will be required, 160 divided by 1000. So, it would so this is the we want to find out basically how much is the saving in the carbon dioxide, carbon from the fossil fuel part. So, this one just so out of this let us say 0.16 kg is what I need for 1 kg of cement. 20% I am using is alternating fuel, that is your biomass, plastic waste, everything put together, biomass, plastic waste or paints waste. And as I said, I just mentioned in couple of class earlier that these are the kind of agricultural waste, agricultural products, industrial, all this municipal solid waste and all that. So, industrial product and all that, and out of this 20% I am using this alternating fuel. So, 0.16 into 0.2, right. So, this is how much it is. This is what I will be using, this much amount I will be using alternating fuel, 20% I am saying, right, is biomass. Sorry, I am using, yes, say out of this right. Now, supposing I am using 20%, so this kg of alternating fuel per kg of clinker. Now, out of this 0.32, let us say 20% is alternate fuel from biomass, and rest has 40% carbon. Only agricultural waste and biomass you are not accounting, but if you are using plastics or something of that kind, that will go into accounting, because this will not get converted into anything else, coal in future or something of that kind. So, this will go in accounting. So, let us say out of this 20% is alternating fuel and rest 80% has got 40% carbon, right. 60% is something else, 60% is something else which might oxidize etc., nitrogen or whatever it is, some might give energy, totally it is giving 160. So, 80 out of this 80%, 60% do not give carbon, 40% is carbon, 40% is carbon, right. So, 20% of 032, 20% of 032, let us calculate, now we can calculate out. So, another 0.2 that I need not account for, because I said if it is biomass. So, total fuel required is 160 kg per ton. For 1 kg I need 0.16, and out of this 20% is alternating fuel, alternate fuel. So, alternative fuel basically. So, alternative fuel basically. So, this is 20 into this much kg of alternative fuel per kg of clinker, alternative fuel per kg of clinker. Now, out of this again 80% is not biomass or agricultural waste, right, 20% is biomass. So, this 20% will not go in my carbon accounting, right. So, this is the alternative fuel, 80% of this has got 40% carbon. So, 80.8 this multiplied by 0.8, this multiplied by 0.8, 0.032 multiplied by 0.8 is the alternative fuel which I must consider for carbon, but it has got 40% carbon. So, again multiply by this, and that will go in accounting. So, you can see how much is the saving. So, you see that is what I am saying, this is what I am saying, this is what I am saying. So, 0.03, 0.2 into 0.8 into 0.4, this is the carbon, and it would produce carbon content, C content straight. Now, unit C produces 44, I mean 12 C produces 44 carbon dioxide. So, 12 C produces 44 carbon dioxide. Therefore, this divide this by 12 multiplied by 44, that will be the carbon dioxide production, because rest all is 0. The other 20% I do not account for them. So, you will have 0.037 kg per kg of clinker from this alternative fuel, right, and which is much less, because this will have now much less, because rest 80%, rest 80% my regular fuel, and from there I can calculate out, depending upon their fuel efficiency and all that, I can calculate out how much is the carbon dioxide they produce. So, in 1 ton of cement, actually otherwise this much would have been this much quantity additional carbon dioxide you would have produced if you are not using biomass, right. So, that is the advantage using this biomass and agricultural waste and all that, and this has got some other kind of advantage, because you do not know, you would have to dump them somewhere. Many of them are not biodegradable, they have to go to incinerator or something. So, supposing you would have put it in incinerator, they would have generated that much amount of carbon dioxide anyway, and for cement production you would have used furnace oil or something else. So, this has got an indirect benefit, where this is your calculation, directly you are getting some benefit out of this. So, this is the small calculation I want to do on the last class. I am just repeating, I think it is very simple, there is nothing complicated in it. Now, let us look into concrete. Let us look into concrete. So, that is what I was saying. During concrete production, during concrete production, supposing you use 1 ton, 1 is to some ratio, there is some waste. So, let us say, I mean just a crude kind of a concrete of the good old days. So, 1 is to 2 is to 4, which would mean 1 is to 6 is your rest of the material except water. So, water is separate, let us say. Now, this would have some wastage also. There you have to add some percentage of wastage. So, if you put all that together, you will get 7.2 tons roughly, it is just one calculation somewhere by somebody, and this in the process will produce some amount of indirect carbon dioxide, because you will be operating some machines, batching plant. Now, if they are diesel operated, they will produce carbon dioxide. If it is in, of course, in a permanent batching plant, you might be using electricity, but then even if you have electricity, you take it from the grid, then proportion of the fossil fuel used in the grid, from that you can actually calculate out. We will see that sometime later on again. So, some amount of carbon dioxide, some amount of NOx, some amount of SO2, etc., particulate matter, this much kg, some solid waste and some liquid waste, because washing, mixer machine washing and all that, there are liquid waste generated, which are treated and handled in a given way. But first, to start with, you will generate all this, and then you produce, supposing like the volume of concrete, it's like you will have something, let us say 300 kg of cement per meter cube of concrete, right, roughly, or 300 or something. So, if I take 1 ton of cement, I will have how much meter cube? 1000 divided by 300, right. I have 1 ton of cement, 300 kg per meter cube of concrete. That is a typical kind of mix for low grade concrete, not a very high strength concrete. The concrete, if you are familiar with those who have done concrete technology, you would know that it is of that order, right. So, even you can calculate this out, very simple, because I said 1:2:4. So, is to, let us say water cement ratio around 0.55 or something of that water, amount of water. So, total material is 6.55, out of that 1 is the cement, mass wise, mass basis, and if I take the density as 2400 of the concrete, 2400 kg per meter cube, in 2400 kg you will have 6.55, divide this by 6.5, that will be the amount of cement. So, this will come somewhere around 250, 260, or maybe less than 300, somewhere around 300, something of that order. So, this is the volume of concrete that you will produce, because 300 kg roughly, I am just saying, you can do exact calculation for actual concrete. So, 300 kg goes in, produces 1 meter cube of concrete. 1000 kg will produce some 3 point something, So, this is not 300, it is possibly taking 280 or something, 280 kg produces 1 meter cube of concrete. You can calculate this out. So, roughly it is of this order. Order will be similar, but it will vary from concrete to concrete. So, it will produce something of this order of the volume of concrete. Then transportation and placement is there. Water you will need some amount, both for mixing water, washing, etc., there are additional water will be required. So, this is not necessarily the water cement ratio, it is more than water required will be much higher than water cement ratio, because there will be wastage, then cleaning water, there are several other water is required in the process. So, put together, let us say this typical values, then it will also generate water vapors 87.7 kg, some rough idea, and then transportation and placement, and then later on demolition and disposal, out of which you will get some amount of rubble. That means, you can crush them, make demolition waste as aggregate out of them, and obviously in the process you would need energy to produce this. So, you can see that cement we have needed energy, well we produce concrete, we also need energy, and that is all. And then transportation and placement, there will be additional energy, because the truck which must be using energy for transportation. So, total energy therefore would be this, all will constitute the embodied energy, and this is the emissions that will come from the concrete, right. So, that is the thing. So, therefore, if I am looking at concrete, I must look at its life cycle energy implications, right. So, initial embodied energy of concrete, and of course, if the life cycle I am looking at, then during the life I might do some repair, which means that some concrete has deteriorated, additional concrete then I have to put in some form or other, the same concrete or maybe a better concrete, right. There are some defect. So, there are some repair required during its life. So, this would be cyclic, in the sense that if I take time and look at the life of the structure, intended design life or planning horizon, whatever in economics you will call it planning horizon when you are looking at the economic analysis, generally you call it intended design life. There is the intention that building or structure would last for that many years. I think I mentioned sometime that bridges might, we notionally take around 100 years or 400 years for dams, 1000 years for possibly atomic reactor building and things like that. So, during that period of time obviously you will have initial, there is some initial energy requirement will be here, initial energy requirement will be here, initial energy requirement, but then you have repair energy from time to time, because repair material will go in, their embodied energy you must take into account. Now, more number of repairs obviously you know the more energy goes into it, I mean more carbon dioxide, everything more resources and so on. So, that is to be also seen. So, during the life cycle, and this can be only with respect to building. If there is an operational energy, for example, you have used a RCC slab in the roof. Now, this will have its own implication in cooling load, right. Supposing instead of RCC of a given kind I use another insulating type of RCC, maybe it will have lightweight aggregate concrete or something of that kind, there its implication will be different. So, this is contribution towards operational energy saving if there is any. So, this we can take in, and all can be expressed in terms of equivalent carbon. We shall see that how we do it, right. All this everything can be expressed in terms of equivalent carbon, simple equation, and that is there. So, let us say embodied energy, initial embodied energy is something like this. Sometime we mentioned that embodied energy of concrete, how much gigajoules per ton. You know, I had a diagram and I said that okay, that is not very large really, that is usually small, but worldwide we use too much of concrete compared to any other material. Therefore, or even in a given building, concrete it contributes maximum to the embodied energy, because quantity used is very large. So, that is the thing. So, anyway, initial embodied energy I can express it in this manner. First, A is this term by B, because I will calculate per unit mass or per unit volume, right. So, therefore, let us see this. So, A is this E stands for embodied energy, subscripts P stands for production, and C stands for T stands for transportation. Now, concrete has got cement. Let us say if I am using some sort of fly ash or something, some supplementary cementitious material, coarser aggregate, fine aggregate, and this is water. So, there are two components in embodied energy. One is the production, another is transportation. Production, another is transportation. Now, production can still be estimated relatively better, but you can estimate it is a laborious job. So, we have to take data from several sites, right, and take data from several sites and then average it out for a given region, given place, etc., etc. Similarly, transportation energy, it will depend upon mode of transportation, right. Now, generally when we talk of cement will be transported from the factory either in bagged or in bulkers, which are pneumatically put into vehicle, closed vehicles, and can be pneumatically pumped out, what we call bulk transport of cement. Cement is also transported by ship if there is a possibility. So, same thing, pneumatically just pump the cement, right, pneumatically pump into the ship tanks, and this will carry, it is done, let us say western coast, Ambuja cement. So, Gujarat Ambuja, the factory is right onto the Ambuja Nagar, which is on the seashore. So, the cement produced is straight away put it in the ship, pumped into the ship pneumatically and transported to Surat, Mumbai or wherever, or even to the eastern coast some places, because it is a cheaper mode of transport, possibly uses less energy too. So, that is what it is. So, this is cement. So, if I have C amount of cement per meter cube of concrete, I am trying to find out per ton. F is the amount of fly ash or something of the other kind, and we are not taking into account the small quantity of admixtures which you use, which would be maybe very small percentage, not more than 2% in any case of the cement, and this is the coarse aggregate. It will have some production energy. So, P stands for production, T subscript is for transport, right. C stands for cement, F any supplementary cementitious material you are using, pozzolana, no, cementitious. Then AC stands for, AC is the coarse aggregate, and this stands for fine aggregate, and this is water. So, AF is fine aggregate, right. So, I think I can erase some of them out. Okay. So, no. So, W stands for water, AF stands for fine aggregate, C cement as I said earlier, and F pozzolans or something of that kind, and AC coarse aggregate. And two components of the embodied energy, transportation and production and transportation for each one of them. So, that is A, the total. I will come to B. ECN is the energy during construction. This is the material embodied energy, and just now we have seen that when you make concrete, you give something like this, this one we just saw 59, this particular case they are saying 5990 megajoules, because you have to do mixing, So, energy ECN will involve ECN there. This will be batching, to start with batching during construction, yes, batching, mixing, right, and transporting the concrete as a mass, from the batching plant to the mold. And also if it is overall concrete element we are looking at, the mold preparation, everything, all those energy will, construction energy will come into mold preparation, reinforcement laying. We are not looking at the steel contribution. If you look at steel contribution, you can calculate out that way. So, this is the total embodied energy that will come, very simple accounting only. And what is B? B is the quantity of cement per meter cube, quantity of supplementary or mineral admixtures, this could be mineral admixtures. I have given you 3 names for this. They can be pozzolans, supplementary cementitious material, or mineral admixtures. They are used, I mean any one other than the cement that you are using, because people use ground granulated blast furnace slag, might use simply limestone powder, some percentage, and that kind of material, right, silica fume and so on, those I talked about. So, E is embodied, so this is what I said, so this is what it is. So, sorry, this etc. Concrete ingredients, right. So, therefore, per unit, this is C per meter cube. So, this is B actually all in kg per meter cube, right, and this was all in kg per meter cube. So, therefore, this if you total mass in 1 meter cube you are actually dividing by, that means you are converting into mass, right. This was the mass, this is cement is mass per meter cube, this is the mass per meter cube, everything is in mass per meter cube, and this total is also mass per meter cube, right. So, you are actually getting per unit mass, in per unit mass what is the amount of energy consumed, that is what initial embodied energy. If you look at life cycle embodied energy, then I got to explain it a little bit more, although I have not put an extra slide there, because this, if those who have done concrete structures durability, then it will be clear. Normally I have not added that slide here, you might you have done a course on concrete technology, then you would have had. If you recollect something like this, we said that concrete is not maintenance free, neither steel. You cannot expect them to remain stable, because thermodynamically we have produced them with the expense of energy, right. So, if I look at that, if the analogy given is if I, because I have produced them with the expense of energy. So, consider analogy given is something like this. This is, let us say, this time, with time, this is with time, this axis is time, and this is what we can put it in terms of Gibbs free energy delta G, or some energy, let us say, let us not use the thermodynamic terms to scare you off, but this some energy you have given to produce. So, you produce something at the expense of energy, means you give delta G, lift it up in terms of chemical potential, right, chemical potential. You see, for example, calcium carbonate, we said that is a stable material, you heat it up to get calcium oxide. So, it will have more energy per mole, it will have more energy per mole, because you have heat it up, right, and carbon dioxide of course will be produced. So, this will have more energy per mole. Now, this energy it will like to dissipate. So, the moment you put together to calcium oxide with water, the material that is available in abundant onto the earth's surface, because that is what everywhere it is there. So, it will form calcium hydroxide readily with heat of evolution, a little bit of there will be heat also. So, slackened lime, and this is also not stable, it will take back some of this carbon dioxide from atmosphere to become calcium carbonate. So, you see the energy that you have given. So, you have actually by giving calcium carbonate or cement you are making, you are doing the same thing, right. Cement you are, steel is available in this form, hematite, magnetite, FeS is not available in Fe, it is never available in Fe in nature, only noble metals are available in nature. For example, gold Au or platinum Pt, they are available in nature. So, they do not react, and there are various ways of looking at their potential, electrochemical potential, tendency to lose electron, etc., all these are there. So, therefore, now this is what you have done. So, they will have a tendency to react. All that you can do is I can put, I have lifted it up and put it over a platform. So, if I put it over a platform, now it will not come down, but it will have a tendency to come down. I mean, somebody pushes it a little bit, it might come down. So, the tendency is always there. Or I can put it over a slope. Instead of doing this, I have decided to put it over a slope, So, I have put it over a slope now. Now, it will come down very, very slowly, relatively faster. This will take infinite time, this will take some time. And then there can be a third situation where I put it in this slope, then it will come faster. These are related to kinetics. This is related to kinetics, right, rate at which it will come out, all right. So, in any case they will deteriorate. Structural elements, because they are mostly made of man-made material, they will tend to deteriorate. So, therefore, therefore you would need to have repairs or occasional repair. So, generally what we see is, if you have a concrete element, let us say you have a concrete element, right, you have a concrete element, let us say some slab or reinforced concrete element, generally reinforced concrete, simple case I am taking, this is a steel bar, reinforced concrete element. Now, there are many deterioration process, there can be many deterioration process, but generally if the deterioration exposes, let us say deterioration process I am not going to discuss here, but I will just mention a couple of them. For example, very common one is the reinforcement corrosion. Now, that occurs because water would have gone into the concrete, also here some aggressive agent like chloride might have come in, or the pH might have changed of the concrete. Normally concrete is of cement hydration produces calcium hydroxide, and there is obviously in cement these materials are always there, sodium and potassium, they are there, Na2, in cement this comes either they are there as impurity as flux, or they will be there everywhere. Sodium, potassium you find, alkali, anything you extract out you find sodium, potassium, some amount will be there. So, they will be there in cement some amount, either coming from raw material or sometime added if required to add a flux, but depending upon situation, I mean I am not talking of sodium alone, I am talking of many oxides. Many things you might add a little bit to control the clinkerization process, and many things might come as impurity, but whatever it is, in cement hydrates you find calcium hydroxide, sodium hydroxide, potassium hydroxide, etc., potassium hydroxide, potassium hydroxide, etc. So, this maintains alkalinity of concrete, and this alkaline concrete protects the rebar because it does not allow active corrosion or deterioration of the concrete to occur. I will not go into the further mechanism of this, but my point here is, if corrosion occurs, what happens is corrosion product will come in the surrounding, corrosion product will come in the surrounding, corrosion product will be formed. This will eat away some of the steels, and this exerts pressure outward. This exerts pressure, and this side material being less, the cracks come here, the cracks will come here, cracks will come here. So, cover concrete is a concrete which will get damaged. If you have alkali aggregate reaction, let us say another reaction nothing to do with the steel, then also the moment the reaction which is an expansive kind of a reaction which causes cracking of concrete, the moment crack exposes the rebar, I must repair it, otherwise reinforcement corrosion will go in a faster way, and concrete can't take tension. So, even structural particular location, if in a conducive condition not repaired long time, it might even show some sort of collapse of elements and things like that. So, the cover concrete is the most vital. In repair, what we do? You replace the cover concrete. So, if I want to estimate the embodied energy of repair, I have to address the cover concrete, and in the extreme case there are two sides covers are there. The at least in a section, any section there could be more, but at least two sides covers should be there in a slab. So, it will be actually 2 or 4 depending upon the situation. In extreme case, let us say I am replacing all the cover concrete. So, this is the cover depth, replace the cover and this is depth of the section multiplied by the time of intended design life, and this is time, one is the repair time and another is I will just come to that back. We will have a break and address some of your question, and we will come back to this, and multiplied by. So, assuming the energy that has gone in, it will be repeated now number of times, but only for the cover concrete, right. So, we will have a small break, take some of your questions and then come back.